All right, guys. So this is what we mentioned at the very end of the last class. So if you have two functions and they match on derivatives, in other words, for each x, the derivatives of those functions are the same, then what can you say about the graphs of those two functions?
That they'll be parallel.
Exactly, beautiful. So they parallel might mean that it's exactly the same function, right? They just or that if there are also different functions, one is either higher or lower than the other, right? And that's very, very important, especially when we talk about the fundamental theorem of calculus. In other words, the functions that match in derivatives cannot be more exotic than one version we found. So for example, we had the derivative equal to 2x, and we guessed that one function that satisfies this is x squared. And therefore, every other function, no matter how weird it might look, let's say if this expression happened to equal to, in its derivative to 2x, then this g had to be of the form x squared plus a constant. Could be x squared plus 0, or x squared plus 5, or x squared minus pi, but essentially it's just the same graph of x squared lifted up or down. Make sense? And that is easy to feel, because derivatives, again, what is the idea of calculus? Very simple idea is that any curve is just a segment or a chain of small line segments. That's right. So every curve is just made of many straight line segments. That's what you use in computer graphics and drawing everywhere, right? So you just, if they're small enough, it will look to you like a perfect curve. And if those line segments are parallel that trace one curve and that trace the other curve because they have the same slopes, then of course we essentially are drawing the same graph, just maybe slightly up in the paper or down in the paper. Good. So and the mean value theorem, which is again a very interesting theorem, makes this idea precise. Okay, makes this idea precise for real numbers. And of course, very sad it is once you get used to this mean value theorem to be dealing with situations where the theorem does not apply. So the mean value theorem does not apply in complex analysis. You have to figure out other arguments. So this is a preview of maybe the last topic we will cover in integration. It's u-substitution. That's what it's called. Now, many things that are named non-descriptively. In other words, the name does not let you see what the idea was. So u-substitution, the name is not revealing what's the idea. So suppose that you found that the derivative of your function is cosine, let's see if you can even do it without my help, cosine x squared times 2x. You with me, guys? The derivative is cosine of x squared times 2x. What was the original function? And even more so, you are familiar with derivatives. What process happened here in this differentiation? What sort of differentiation rules were applied?
This has to do with the previous classes, if I recall, with you're asking us to do basically how to, with the jellyfish and whatnot and all that, right?
Great, brilliant. And its name is chain rule, right?
Chain rule, thank you.
I don't know why. I mean, I suppose because you see chains of products. If you have a sort of horror-driven mind, maybe you think of Texas Chainsaw Massacre because you are cutting the fish. Differentiating, it's like, again, in some loose analogy, it's like cutting, and then you find another smaller fish and you cut that as well, right? But again, I think simply it's called chain rule because you have products of derivatives, right? So it's chain rule. And what you call u-substitution is therefore just the reversal of chain rule. Good? Original function is beautiful, Alexander. It's sine of x squared, right? And what do you observe, right? You observe that, okay, this is the inner function. I call it this way. I call it bx, it's the big fish. And here the cosine is this filleted big fish, whereas sx is the small fish. And you see that it's the derivative of the big fish that has in its belly the small fish, right? And that's what would come out. In other words, when you do reverse chain rule, you can ignore for a moment the inner function, because here is the inner function is derivative. You just have to find or guess the antiderivative of the outermost function, right? Because what did you begin? This is just the derivative of the outermost function. You find x squared in its belly, and then here you have to find the derivative here. So all you have to do is just guess that the derivative of sine is cosine. Good. So here is how I view this, right? In our case, it's the derivative cosine is the big fish differentiated, x squared is the small fish, and s prime x is the derivative of the small fish. And all I have to figure out is just the antiderivative of b prime here. And as Alexandra correctly mentioned, this is simply sine x squared plus a c, right? The constant you just had to indicate that it could be higher than sine x squared or lower than sine x squared. Here is a very similar question. Now suppose the derivative is cosine x squared times x. What do you do now?
Oh, you do the last one was just sine x squared.
The last one was simply sine x squared, correct?
So it's half sine x squared now.
That's wonderful, right? So, but here you see, if it's sine of x squared, the derivative will be cosine x squared times 2x. But here I only have x popping out, okay? So this looks almost like the chain rule, but it's not quite complete. Yes, there is some strangeness about it. It's not quite chain rule. But so what you do, you have to figure what you call wishful thinking. Now, wishful thinking is this is what you wanted to see. You wanted to see a 2x here. Again, what happens here? Two things happen here. You recognize what process happened here. And then you see that maybe the expression here is slightly an incorrect process. You see, our class, once you get used to it, there are not so many concepts. It's mostly we have like one or two concepts and then recognition that something is a distorted version of what we just learned. So cosine x squared times x is a distorted derivative where we have a chain, right? So here I see x squared, so that's my inner function. I have to feel where's the inner function, right? And here I see the derivative of the inner function, but it's missing a 2. So I put in a 2 and I compensate. I put 1/2. Understand? So I see 2 and 1/2. And then I know that derivatives can commute through any constant. So I have to now guess is the antiderivative of cosine, which is sine x squared times 1/2. Does it make sense? You see what I did? I introduced the term to make it a complete derivative of the inner function, and I multiplied by a constant to compensate, because I cannot just put things into my expression that were not originally there. So 2 times 1/2 cancel to 1. So now I have 1/2 sine x squared plus c. Make sense? Simple. I'm hoping that the way I will teach you, here I haven't yet prepared too many examples, you will not use u-substitution. It's all not very useful except for some situations. You can do it in your head much faster. Okay, but some situations make it better. Okay, so first of all, I would like to just pause for a moment and mention that usually you don't ask the problem as f prime x equals something. You just say integral of some expression, and we will learn later what's the point of this notation. But if you see this notation, that means find antiderivative of this expression. Okay, so for example, if you see integral of 3x squared dx, it's called the indefinite integral. Not yet. It's not yet the area under the curve because there are no bounds. What this is just saying, and we'll see why we use the same symbol as for area under the curve, right? Later, once I talk about fundamental theorem of calculus. What I see here is simply a strange language, but it's requesting to find the original function. The derivative of that original function was 3x squared. What is the original function? And you can quickly guess that it's x cubed plus c, right? So it's basically just a language, mathematical notation for asking a question that you hopefully know how to solve. Good? And for example, the integral of 5x squared plus e to the x, this is simply asking, find the antiderivative of this expression, yes? Which is then 5 over 3x cubed plus e to the x plus c. Cool? Now, you can notice several properties of antiderivatives. So the antiderivative of a sum of two functions is the antiderivative of first function plus the antiderivative of second function. Why is that so? Because derivative of sum is sum of derivatives. So reversing that makes sense to work on each part separately. You understand what I'm saying? So this is just an obvious statement if you realize that it's just another way of speaking, maybe a passive way. I'm not quite sure grammatically how to say that, but it's a reverse way of speaking about the fact that the derivative of sum is sum of derivatives, right? So that means if I find antiderivative of first function and add to it the antiderivative of second function, the sum of those antiderivatives ends up being the antiderivative of f plus g. I say there, but of course it's plus a constant. Geometrically, I can say there. There is only one geometric shape that has globally the same derivative. That satisfies a particular derivative equation, okay? A similar property is that I can move the constant outside the integral sign. And that's really just because if I can figure antiderivative of this function f and multiply it by a constant, derivative just will skip the constant, right? We have this constant.
Simply just like reversing the.
Yes, you are simply reversing. If you notice that notice the patterns. We do the same thing for exponential functions and logarithms. So many properties they are really just expressions of the same property, right? The property of logarithms and the property of exponential functions are just two ways of describing the same thing. The exponential function geometrically and the logarithm are the same curve, right? It just depending on how you view the astronaut analogy, understand? So good. So let's play this game, guys. See how good you are at guessing antiderivatives where those are slightly more challenging. Here is A, B, C, D. See if you can answer A, B, C, and D as quickly as you can. What is the antiderivative of this expression, of that expression, and onwards? You can see it, yes? Can I move? Yeah, I can. Here, I will. Just I don't want to reveal what's below. I'll be right back.
Yeah, I don't know how to do this.
The first thing you try when you're stuck and you were first, what's the most you realize? You see, if this came as a derivative, can you identify what operation might have made it a derivative? You understand? You're reversing differentiation, so can you identify what happened here, right? And probably you'll find the analogy weird or maybe useless, but imagine you're a detective and you're solving a murder crime, right? So you come to the murder crime and somebody asks you who did it, and you say, I don't know. But you don't stop there, right? You do know something. You might see, let's say it was, what sort of pistol was used, what sort of ropes.
Professor?
Yeah.
So I remember like you want to like find when it comes to something problem like this, want to find. I forgot. It's like, let's say for example, right now, we have, you see the square root of x third plus 1.
Mm-hmm.
Do you
Yes.
take does the cube have a major significance in the overall function?
Well,
in a way, like I'm trying to.
I think you might. Well, I mean, you might have the idea, but what you are saying, what you're phrasing is, what is major significance? What do you mean? Right. So you understand my analogy of solving a crime. You don't have to necessarily figure everything right away, but can you tell me in this case, what differentiation rule might have produced this expression? Can you figure that one out? Okay, when you can figure what differentiation rule, it's like figuring the caliber of weapon used in a murder, right? You know something about it.
Are you doing the power rule?
Well, maybe. That's the question. But you did the beginning. What do you mean by that? So what's the beginning?
So I started, I don't know, 1/3 x to the third, and times, I think this is wrong, 2/3.
Well, before you finish the operation, well, you are absolutely right. It's undoing chain rule, but that means you realize this chain rule. You understand why I'm speaking about a crime? Here is, I think, one thing that some people do and some others don't necessarily do, right? So there are many questions I cannot solve, but then at least I see what can I say about the situation. Even if I cannot solve it, what's the most I can say? And then you can progress, okay? So you look at the situation. If you cannot figure the antiderivative right away, and that's very fine, many of them are difficult, you ask yourself, what do I know about it? Do I realize how such expressions might have come as a result of derivative? Okay. And in a moment, I will show you. Okay. So I'll wait maybe 1-2 more minutes. If you don't see the process, I will show you the process. And you can already see Abdul mentioned. It's like undoing the chain rule, which means that Abdul realizes that this derivative expression came as a result of chain rule.
Yeah, I don't know what to do here.
All right, so let's work through problem A. So here is what I realize in problem A, right? I look at I scan and I see there is a root, and underneath the root is not x, right? I mean, I think I have like what, a few functions that I'm familiar with. I have sine, cosine, tangent. You have trig of x. You have roots. You have numbers to, you know, x to some power n. Nothing that special, right? E to the power of x, whatnot. We just have only very few types of functions. So here I see root, and underneath the root there is no x, something else, which means the root, if it's a medusa or whatnot, it has been eating something, right? It has eaten a polynomial x cubed plus 1. Good. And look what I see over here. It's very non-coincidental. This is x cubed plus 1, and this is x squared. Okay. If this were another number, let's say x to the power of 7, it would have been possibly a very difficult problem, or a much more difficult problem than this one is, right? What? Because look at it, x cubed plus 1, and here I see x squared. Well, take the derivative of x cubed plus 1, you'll get what? 3x squared, correct? The 3 will drop down. So what I see is my eyes scan it, and I see inner function and the derivative of inner function.
Yeah, that's what I was saying. Okay, so I'm on the right track. Okay.
You are. If that's what you were thinking. Well, I understand you were speaking about is there significance of x cubed, but not so, but you, yes, you have to phrase it. That's what I mentioned, right? So
I know, it's just not easy for me, that's all.
that's fine. That's just the beginning. So you understand that now I look at it and it's not a complete chain rule because I'm missing a 3. You agree?
Yes.
I'm missing a 3. So here I put this 3 that I'm missing, and I multiply by 1/3 because I don't have that 3. I need to cancel it, right? So I multiply by 1/3, and I use the property that I can move it outside of the integral sign. Make sense? And then what am I truly anti-differentiating? So if you don't see it, root is just the power of 1/2. So it's something to the power of 1/2. What's the antiderivative of something to the power of 1/2? It's 1/2 plus 1 divided by the same thing, right? So 1/2 plus 1 is 3/2. So the antiderivative of just root alone is 3/2. Inside I have x cubed plus 1, and 3/2 must be cancelled with 2/3. And then I have this 1/3 from outside that I multiply back. Make sense? So the 1/3 comes in only because I had to correct it. I made what's inside of this integral sign, I made it look like a perfect chain rule where the outer function was root, and antiderivative of root is 3/2 times 2/3, and you put what's in the belly, and that's it, you're done. We'll see, make sense? So it's 2/9 x cubed plus 1 to the power of 3/2. All right, but so where have I lost you? What doesn't make sense?
I did almost everything correct, but I don't know where your x went, like disappear. You see over here, you wrote 3x squared, but where's the x? That's
what do you mean? Where is the x? So I don't need an x. I just what I see is this, right? I see the outer function. I see the root function as eaten this polynomial. Yes.
right.
And here I see the derivative of that polynomial. Usually, the way I wrote it, I would write it on the right, but multiplication is commutative. I can write the derivative in front, or on in front of the expression, or at the back of the expression. So what I do is essentially I realize it's chain rule, and to reverse chain rule, I realize I only need to find the antiderivative of the outermost function.
Oh, okay.
You understand? So it's not algebra that I'm doing. It's just I realize what happens in chain rule, right? You can see me. Let's say I'll scroll to myself so I can see me. Right? So what happens is here is my function inside. Inside it has some other function that it has eaten. When I take the derivative, it's like the derivative of the outer function, and I find this inner guy times the derivative of the inner guy, right? So then when I reverse it, I ignore the derivative of the inner guy. It's like I reverse it also, and I'll have this undifferentiated inner guy, and I close or anti-differentiate the outermost function. You understand? So in other words, I realize that I just have to find the antiderivative of the root, and I'm done. Okay?
I understand. I think I did B already.
Okay, so wonderful.
C. I did C. B is B I didn't do. I did C.
Well, let's wait. Let's do B now, guys. Right now, your goal is to solve B. Let's see how quickly you can do that. Okay. Solve B, and then we'll move to C. Let's see what's that.
How fast should this actually take us? Because I'm a little concerned with the amount of time it's taking me.
No, but you're just introduced to it. It will take you a long time when you're introduced, but hopefully if you pick up, you see, I developed some of my techniques over time, right? It took me first longer, then faster and faster and faster. I mean, I had many, I cannot even imagine how much time I had practicing those things. When I was first learning it, I practiced 4 hours a day. That's what I told you, right? But that was already years and years ago. Right, so I wonder if you were born when I was practicing it.
Probably.
So, yes.
Is it cosine cubed theta?
Careful, right? First,
I'm asking if the question says that.
Cosine cubed, of course, times sine theta.
Okay, good.
Certainly, if you learn it my way, you will do it faster than, I'll teach you how the textbook makes you do that later. But if you learn it my way, many people that learn it well would prefer to use this.
Yeah, I'm trying to catch on now.
Is it 1/2 cosine squared?
Careful, careful. I think you want to go the other way around, right? So
So if it's not that, then it's 1 over negative. Is it negative also, by the way?
Yes. But most importantly, you look at it.
Wrong.
No, well, I think you differentiated instead of integrating.
Oh, okay then. Yeah, then I'm still. I guess I'm still lost.
All right. Here is, guys. You see, you look at this expression, right? You look at the expression b, and what? Basically speaking, right? Im Grunde genommen, as they say, taken at the ground. What am I integrating here? You see, I don't see cosine cube times sine theta. What am I integrating it? What do I see? In the previous question, what was I integrating really? I was finding the antiderivative of what? Not this expression. That's just that obscures my recognition, my eyesight. What was I truly integrating? Look at it. I'm pointing to it.
Okay.
The square root.
The square root, exactly, right? If you will not be confused, I was integrating the square root of x, or
so
the
for
square
this one,
root of
you're integrating the inner function, which is cosine theta.
Well, not the inner function. Inner function is coincidental, right? What am I integrating is?
The square root of x.
Here, the square root of x, precisely, right? Or if you, that's why it's called u-substitution. Really, it's the square root of u, so that there is no confusion. X here has a different meaning, right? I just want to say I'm integrating this thing. So I say I integrate the square root of u, okay? It's completely coincidental. X, u is just a description, right? What am I integrating in b?
Sine theta.
Say it again.
Sine.
Fine.
1 second, one at a time. David, say what you were saying.
Sine theta.
What do you want to say, Sarah?
Cosine, no?
I said sine, but now I think it's cosine because you said
No.
Really?
It's
No.
cosine theta. It's
You are
cosine-
well. Abdul solved it, and he's correct. But my question is, for the others, what am I really integrating? You understand the difference? Why can I do it so very fast? Because I see what I'm integrating better than you. Not literally, right? I don't see theta or cosine or sine, etc. I just look at it and I see, I'm integrating something much simpler. What am I integrating here, truly?
Theta?
Cosine cube theta.
No. Well, that's too complicated,
Is
right?
it just theta?
No.
Theta.
Yes,
I
again, recognition, guys, right? You see what you're telling me
Okay.
is this, right? I try to make you describe something, and here is a mustache. You say mustache, nose, eyes, right? Left eye, right eye, brows, here, right? But you're not telling me more specifically. You're not. There is one nice word, right? If I had this
cube?
mustache,
The cubed part.
if I have this mustache, and I put this here, what am I? That doesn't matter. But
Nice.
what am I?
Oh.
Or if you need, okay, I do this. What am I?
You're
you right away.
I know this one. I know this one. I know this one.
He knows this one.
Good, right? So raise your hand if you know this one. So you see, this when you describe, you see, look at it. I do this. It's a very silly thing, but you right away know what am I referring to, right? Right away. What do you say, right? You don't say nose, eyes, mouth, right, shirt. You right away might imagine. What do you imagine? I wonder.
I imagine Hitler.
Exactly. Here you go, right? Now, what's happening in this situation is very, very similar. I'm asking you, what is this expression? Right? You see, obviously with this gesture, machines will not be able to easily understand it.
So you're saying look at the bigger picture, don't look at it.
I am saying look at the meaning, right? Bigger picture, sure. A meaning. Tell me, what am I integrating here? Sorry for my weird analogies, but
I like them.
My analogies usually come with either very offensive stories because I find them funny, right, or very trite stories, right? So let's say. So I'm so obsessed about it. If you look at my exam in combinatorics, it's like there is a very difficult question that I realized is just a story about political correctness, which I find extremely funny. So I understand mathematical formulas because I understand something about political correctness, or I don't, right? So two ways to think of it. So similarly, B, what is truly happening here? What am I integrating? Come on, guys, right? You can do it. No? No? Should I tell you?
Yes, tell me.
Okay, I'm just integrating x cubed.
What the freak?
You can curse. It's okay. I don't mind. All right.
Yeah, but where's the x?
It doesn't matter. There is no x. You see, when I say x cube, it's just an
That's an
expression. I'm
alphabet, like-
integrating the cube function. All right. Just
Oh,
like
so-
I pointed over here, right? It doesn't matter x or I'm integrating u cubed, whatever you like calling it, right? When you say x, again, guys, it's just a convenience of speech. There is no such thing as an x. You understand? It's just a letter to refer to. It's just there is no such thing as a person, right? What is a person? But L is a person. David is a person. Joel is a person, Sarah is a person, Arham is a person, right? But there is no such thing as a person. It's an abstraction. A person is a variable that somehow allows me to talk about all of you with one word. You understand? It's just a convenience. Similarly here, there is no such thing as theta or x. Those are just letters. There is just the meaning. Similarly, when you read this word, you don't read D, E, R, I, V, etc. Right? You are just seeing the word. And then it creates certain
So can
images.
I ask you a question for C? We're integrating e to the x?
No.
Great. X?
No.
God.
So you see, what is the answer immediately here? So there is this derivative of cosine is minus sign. So that's why Abdul was correct in putting a minus sign over here.
Yeah, I got the minus part.
Yes, let me show you what happens here. You see, when I break it, I see that cosine of theta is inner. And then the derivative of inner is minus sign. So I put a minus and I put a minus, right? That's roughly how I see. And now I see what? Look at it. The inner function is somewhat coincidental because when I reverse chain rule, what do I need to do? I just have to reverse the derivative of the outer function. I already have the inner function sitting in its belly.
I did it backwards.
So what you have now is minus 1/4 cosine to the 4th power theta. But why is it minus 1/4? The minus is the minus over here. It's just what you call it a corrective lens, like putting glasses, right? So that it will be a perfect chain rule. To be a perfect chain rule, this requires a minus here, yes? So I have 1/4 cosine to the power of 4. But really what I integrated is x to the 3rd power, or u to the 3rd power if you don't like the word x, right? Or better said, the cube function. Okay, so what in this expression am I integrating?
The x power.
Not
function.
clear. What am I integrating here, guys? You see, guys, in other contexts, you understand it perfectly well, what I'm talking about.
Is it x?
No, and Abdul, it's not e to the x, right? Because first of all, the function I need to find antiderivative for is the outer function, is the function that ate all others, right? It's the biggest function here, so to speak.
Cosine or e? One of
exactly. So what are you saying, Sarah?
those. It's either cosine or e.
Well, so possibly, but
the
so what is it?
Cosine,
what is it?
And the answer is sine e to the x.
Brilliant. The answer is sine e to the x. Because what? Because Abdul and Joel, you are integrating the outer function, and the outer function is cosine. So this integral might look more complicated, but I truly only see cosine. So I see integrate cosine. That's all I see. Because it came as a chain rule. I need this will disappear. Derivative of e to the x is e to the x. Okay. So all it is, it's like a lesson in anatomy. You have to realize what is the function that sits in the belly, and you can ignore that function, and then you just sew back together the outer, the bigger function. It's like you're putting things back together. Does it make sense?
Yeah.
Good. Anyone it does not make sense to yet? Should I say more? If so, let's see what's D. Tell me, please, what is the answer to D? So this comes with practice. You just have
Are you
to
integrating Z squared?
Why?
I don't know. I'm out of this one.
I thought that, but then I'm like, why shouldn't it be z third plus 1 then? It wouldn't make.
You
Yeah.
understand, guys? When you do this procedure, again, what I imagine is, again, sewing together a cadaver, or like in an anatomy class, or maybe putting Jack back into his box. For example, I imagine Jack is out of the box, I push him into the box and I close the box, right? So those are the ideas that come to me, right? Or anatomy, so you have the belly is open, stuff is out, I'm pushing it together and I'm sewing it together. So when you do that, in other words, you have to realize what is the opened outer function.
I think it's something we did ln.
Wonderful, better, wonderful.
Because there is 1 over something times
Beautiful,
something.
beautiful. But I think you are seeing.
You know, I listened to your suggestion and I watched this, the Professor Suzuki.
You watch Professor Suzuki.
And he has super short videos, very helpful.
Yeah, they're helpful.
Like
I should
6 minutes.
Yeah, true.
So today I was watching almost all of them.
Does he have lectures on calculus?
Refresh. Yes, those for calculus, but super small. He used like super short.
Yeah, of course, because people have short attention spans. It has to be, I think, 10 minutes or shorter for people to.
Yeah, like 6-7 minutes.
Exactly, right?
Yeah.
Exactly. Right. I should send me the link to the videos. I'll send it to other people. Maybe they'll find it useful.
Okay, sure.
Sure. You see how excited you are? 6 minutes. Ooh.
I did so many of them. I already finished 3 notebooks for this class.
Okay,
Same.
cool.
Me too.
So for this integral, guys, right? So,
Wait, let me write it down.
Yeah, go ahead, write it down, and maybe you will explain.
I'm just gonna follow along. Also, today I'm not in my own head.
That's fine.
Yeah.
Like, yeah, you can figure it out. Just again, don't give up with it. Don't give up on it. I'm sorry.
By the way, Professor.
Why not? Absolute value is possible. When you anti-differentiate a certain function, you see ln is only defined for positive values inside of it, right? So if you put absolute value, that makes it defined for a bigger range of values. Yes. What did you want to say? What did you want to say, Joel?
While they're figuring out the question, I'm not bothering now. I'm gonna wait till you explain it. About the tests, how is it working? I'm sorry, I'm just like asking over and over. I know we discussed it many times.
And when is it?
When is the second exam? I mean, I should post it now. You see, I would have posted it a while ago. It's just a futile feeling is that I would like people to know something, right? And I'm thinking whatever I do, let's say I post the exams, people just.
So, if you post the exams tonight, when is it due?
I will post them tonight. Well, I would say those exams are designed to be solved in 2 hours. I would probably want them to be done by next week. I can give longer time, but again, you see, longer time might mean again that people don't do it, and they end up having people are not rational about how they use their time. If they feel pressure, somehow they do things. Most people, I don't know. If they don't feel pressure, they don't do anything until the very last moment.
So it's the same format as last time. What is it?
Yes, it's the same format as last time.
So why do we have to create an account for this guy?
Because you're taking a timed final exam.
Oh, I hear. So it's gonna be.
So how it's gonna work? Truly, I'm sure you know better than I do. So it's a timed exam. The advantages, of course, are that I thought of building such a thing is that I don't have to grade anything. It's just automatically, I suppose. I'm hoping, right?
It's multiple choice?
I assume, again, guys, it's all my assumptions. If it is an exam that I afterwards have to grade, I would not be especially happy. Usually when you use computers, it's like multiple choice, or sometimes you put a number in and maybe you have like 3 trials and whatnot.
So it's not your exam?
It is not my exam, correct.
Okay.
It has never been not my exam. We'll see, guys.
Would you still want us, some of you guys might hate me for asking, would you still want us to like reach out to you and explain how we did these examples, or are you going to call us?
Well, I suppose if you have a timed exam, it precludes my need to bother you. Besides, I thought of calling you. You see,
lie,
I can tell you why I have not called you just so far. You know, I am honestly afraid to find out how little you know, because
Yeah,
I mean,
so
I cannot always tell immediately whether you copied or not, but I can very, very quickly tell how much you know, and
So,
that's the
I'm
problem.
not gonna lie to you. I'm very nervous, and you might think I shouldn't be because I've been following along, and I've thought myself like I'm doing well in your class. Like I'm figuring things out. Sometimes without even a paper. Sometimes without even using my pencil. But at the same time, when I go back and we're done the session. I have to go and help my family, and then I come back upstairs, and then I get back into the work, and then I find problems to solve, and I'm just like, what on earth am I doing?
Mm-hmm.
Well,
I look back at the notes even, and sometimes I'm just like, what on earth is going on? Is it okay if I reach out to you?
You can try reaching, and I will try as much as I can to answer. I'm myself somewhat overwhelmed. You see, I mean, I write the lectures, I present them right.
They're good, they're great. I understand the concepts, but at the same time, it's like sometimes I just freeze, and I'm just like,
I understand, guys. So relax about it. You're okay. So let me just go. Let me go to this thing, and we can talk again. We can talk after class as much as you. What about it? No, I like your question. I hope that it's the others. I think you are too obsessed about the grade, which to me makes no.
It's not. No. I'm obsessed with the subject. You know, I like the math. You know, I like the material. You know, I like the concepts. You know, I do. I've spoken to you plenty of times and explained that to you.
I mean,
the grade at the end of the day, it doesn't matter because in the end of the day,
it does. I mean, I know it.
I understand. I'm not upset at you at all. The thing I'm just a little stressed. The point is that you can give me a B in the end of the day, or a D or a C, but the point is because I can just do credit or no credit this semester. So there's really no worry about a grade in the semester during the semester. I can get a C for every single class, even though I hate that, and I could just file for credit, and that's it. And you know what? I'm still gonna have a 4.0 in the school. It's my first semester. That's
good. That's good. So I will, guys. For any of you interested in whatever the philosophy of grades and the class, etc., I can say much more about it after this lecture if you're willing to stay.
Yeah, that would be helpful.
But yes, again, philosophy. Again, I'm not likely to convince anybody of anything, but I can tell you this: I went through many years of college and school, and I've taken many classes. I've almost completed a degree in psychology. I almost completed a degree in philosophy. I have almost completed a degree in psychology and philosophy. I had a degree in German and all sorts of other things. Wow. Again, right? All of it. You see, what did I truly learn? What I truly learned is maybe mathematics, maybe German a little bit, right? Because again, all the other classes, memorize this, write that. If you learn the subject, you might come up with something. Who knows if it will ever be useful to you? Exactly, it's thinking that's useful, really. But you can come up with something that's actually worth having. I think with many other subjects, you will come up with nothing whatsoever. So if you get to love this, if you get to pursue it, if it gets to occupy. And it can be affecting your life in many ways in which you would never have predicted, for the best or for the worst. And again, we'll talk about it later. Let's get to the problem. I'm sorry, guys, for my segues. So that question was here, right? All I have to do, and Abdul, you're correct, and Batel, actually we did it, right? We have D now, right? So I realized that I can write it as z squared times 1 over z cubed plus 1, which looks like 1 over something, right? It looks like 1 over x has eaten z cubed plus 1, because here you see z squared. And z squared is almost the derivative of z cubed plus 1, right? I just need to write here 3z squared. I need to put a 3 here, yes? So I have 3z squared, 1 over this, and then I put a 1/3 to correct for the 3 that I introduced. So what it is really, it's really the integral of 1 over x, which is a ln of absolute value. But x here is this guy. Make sense? So instead of seeing this much more complicated looking expression, I really see the integral of 1 over x. You follow? Yeah. 1 over x. Okay. Good. And here is an exercise. How are those questions constructed? Here is how I construct those questions. Place something in the box. Here is a box to make the derivative very simple. Let's see what you would tell me. You can place something into this box to make the derivative very simple.
Well, simply what we did before for this one would be simple. Is going to be you're going to put 3 3x squared. That's the most easy thing, no?
Wonderful. Except you can put a 0, right? But 0 is not,
not
what I'm looking for. If you put a 0,
practical.
right? No, it is. I mean, my point is to train you to realize what's chain rule, right? So this, if the integral were of sine x cubed dx, that would be a very difficult integral. I think those are called Fresnel integrals. They have to do with
3x
mirrors.
squared would be what?
Sine of x cubed, right? Those are those types of integrals are not simple integrals at all. They are called Fresnel integrals. They come in optics. But if I put something in here, you see, sine of x cubed to find antiderivative for is very difficult. But I can place something here, and the integral will be very simple.
Yeah,
and
because
yeah. So you see, this guy comes out when they take the derivative. This guy comes out, and it will be 3x squared that I want to place here. Yes. If I place 3x squared, the integral would be what? So place here 3x squared and tell me what's the integral. For the next question, Joel, I want to see if others understand. You can think, but don't right away tell me. Right. So
the answer for the first one, you're saying we should put 3x squared there and
then tell me what's the answer. Yes, and then we'll go to B.
You don't even need to put 3x squared to compute it.
Well, I mean, if you don't put something in this box, then how do you find the antiderivative, right? So you look at this thing and you think, well, something should be here to make this very, very simple. And what should be here? You said yourself 3x squared, because if this 3x squared, this has come from chain rule. And if I put 3x squared, then what am I truly integrating? There is a really great
x cubed.
No.
See, this is where I'm not hopping. I'm not getting the kishkas.
The outer function we're integrating, right? You realize that what happens.
So sine.
Exactly.
There you go.
It's like Jack in the box. What are you closing? When you say what are you integrating, I think what are you closing? You're closing the box, okay? X cubed is the Jack that pops out and becomes the 3x squared, and the box is sine. I need to close or anti-differentiate.
I understand. Okay.
I hope my analogies are. I mean, that's how I think truly, but I'm not sure if they're helpful.
So you're saying in the box it's gonna be sine?
No, the box is sine. When I do u-substitution, whatever, you'll see why it's called u-substitution later. But
okay,
really because I'm integrating sine of u here. That's why it's called. The u is
so you're working backwards.
Yes, you're working backwards.
Then you have negative cosine.
Negative cosine of
x cubed.
Precisely, plus c. Brilliant. Right? You understand? So you close the box, right? So chain rule is like the box was opened, it was the outer function differentiated, and Jack came out. So Jack coming out is 3x squared. You now close the box. So Jack can be ignored. Essentially, you're closing the box.
right.
That means you're taking the antiderivative of sine, which is minus cosine. So, right? So, yes.
Give me a second.
And then for tan.
Yeah, so that now for B. So you see this, you all understand, yes, guys, right?
Yeah.
You all got why this first line is simply minus cosine x cubed, yes?
It's the derivative of sine x cubed.
Right.
No,
it's well, antiderivative, yes. So it would be
Okay.
minus cosine of x cubed. Now tell me what should you place in this box in B to make the problem very simple. And again, don't shout out even if excited. I want to see that that everybody gets it. Well, most of you are silent, guys. I hope you're not sleeping. I wish I had some sort of pulse measuring device.
We're alive.
I think I got it.
Okay, wait, and
I'm not saying anything. I'm not saying anything. I'm not saying shit.
Okay. So guys, I like the phrase "im Grunde genommen," taken, so to speak, at its base. I'm not sure what the corresponding English expression. taken at space, right? So in other words, when I look at this thing and you say, what's the tachlis? What's the gist?
Tachlis, there you go.
But that's not English. That's what? That's Hebrew.
Well, I understand it, I guess.
Right, tachlis is also kind of good.
Like, what's the conclusion?
Not the conclusion. What's holding it?
What's the point, maybe, right? But
I'm
I don't
saying like
this.
what's holding it all together in a way.
Well, people say what's the point, but that has ambiguous meaning, right? What's the point meaning? And maybe I don't want to do it.
Yeah, what's the point of this? That's basically what that's something else.
Mm-hmm. So tachlis or im Grunde genommen.
Yalla.
Okay, so yalla means what? Are you ready, guys? That means you want to the answer?
I'm not. I don't know.
You Batel, you say yalla, so it means that you're ready.
Because I don't know the answer, and I want to know the answer, and
No,
I'm struggling.
Can I ask?
So what do you place here?
Can I ask something first?
Okay, go ahead.
Is it possible to know what we're integrating before we even put down what's in the box?
Well, this question is how those problems are constructed in a way, right? So I'm trying to train you to see what goes in here. So
can it be e to the x?
Yes, what we're integrating is e to the x. So, but to make that true, we need to put something in this box. We need to put jack. What is jack here?
Oh.
What's the inverse of?
Even if you don't remember it, tell me what is it that I'm placing here. You see, I know you need to give me the full answer, at least part of it. What am I? What is it that I'm putting here?
1 plus x squared.
Right. Yeah, but no, David, that's not the answer.
It would be the inverse of inverse tan, which is
1 over plus
negative.
Just a second. Let me listen to what's I want to see what Sarah is saying. Tell me, Sarah, what are you saying?
I'm trying to figure out the inverse of inverse tan, which.
But why do you need to find inverse? So what is it that we place? What is it we do? We are undoing what operation?
We're undoing what we just did, right? So wouldn't that be negative?
Complicated. Undoing what we did will confuse you very, very quickly. We are undoing what?
The tan, -1. E tan to -1x. That one. That's
we are undoing chain rule.
Okay.
U-substitution is reverse chain rule. Undoing chain rule, which means what I see here is that an open box and jack is out, which means derivative of outer function, that's the open box.
Yeah, now we're trying
multiplied by the derivative of the inner function.
Correct.
So what should I place here?
Say again.
You say again.
No, you.
We're trying to put the outside into the inside box, right?
Yes.
Because this is the outcome, right? We're trying to find what we got. What was it before we got this, right?
Yes.
Okay.
I hear. You're thinking good, Sarah.
Thank you. I'm trying. I'm really trying.
You're giving me. I'm shepping nachas here.
Thank you.
So, guys.
Is that box the derivative of inverse tangent?
Beautiful. That's what I was waiting to hear, David. The derivative of inverse tangent. Because that's with my jack, right? The inner function is tangent inverse. Here I should see the derivative of inverse tangent.
Right. So what is that? What is that's my question? What was it?
The derivative of inverse tangent?
Yeah, that was my question because I know.
But that's the next thing. How now derive it yourself. I would have.
I knew the inside has to be the derivative of inverse tan, but I don't.
Beautiful, but you didn't say that. I believe.
I said it.
The inverse of
No, when you say the inverse of inverse tangent, the answer to that is tangent. That's not what you were saying.
Right. So you want the derivative of inverse tan.
Yeah,
exactly.
And that's easy. Then it's 1 over.
Don't tell me, guys, that you were saying.
I said it's 1 over 10. I'm so confused.
No, it's the derivative of the inverse of tangent. Okay.
Okay, Sarah. I'm so sorry. It's you're somewhat correct. It's 1 over tangent of tangent inverse. Right? Sorry, it's 1 over.
Brilliant.
Careful.
Okay.
It's
I'm getting more confused.
What's it?
1 over tangent over inverse tangent.
1 over.
No. 1 over the derivative of tangent evaluated at inverse tangent. The derivative of tangent is secant squared. Right? When you forget, guys, you derive it right away. That's how you train, right? Say this is the question and you have no cheat sheet, nothing. That's what I would do. What's the derivative of tangent inverse? Right away establish, right? So you train, and so that it's like a tree with many roots or many connections.
Can you just put
recover
the derivative of tangent inverse?
The derivative of tangent inverse is 1 over 1 plus x squared.
That's fine, no?
So what you place here is 1 over 1 plus x squared. That's the derivative of tangent inverse. Make sure that you can establish it, guys. It's not by memory, right? You need to figure out how to, if you forget
step by
something,
step.
how to figure the answer. So the answer is now e to the tangent inverse plus c. You understand?
Okay, so don't jump, just go step by step.
Okay, if that's what you call. In other words, if you don't know part of it, just figure it out, right? You can reconstruct it, and then it will be very familiar to you. Anyhow, so let's move to.
I have a question.
Go ahead. Go ahead.
Why do we need to figure out what's in the box?
Again, it's
e
we're undoing
to the inverse tangent, so whatever is e, the derivative for it is the same thing.
What I'm trying to say is this. This is not an exercise in actually solving the derivative. I'm showing you truly how to watch, right? So I'm showing you what to do here, right? So the question would have been written like this. I'm trying to show you how this question is constructed, you see? So usually you already told what's in the box, but I'm trying to train your eyes to see what must be in the box. You see, to recognize the inner function, outer function. That's pretty much
We're
how
looking for the actual question.
Right, so we are looking for the outer function. We want to understand how do I recognize the inner function, the outer function. You see, so in the box, I would place the derivative of the inner function. And then the outer function is, in this case, sine. Here, the outer function, the derivative of the outer function is sine. The derivative of the outer function is e to the power something, right? Okay, so now let's move to the next lecture. Okay, so the next lecture is area under curve. Hopefully we'll cover at least a little bit. And before I begin talking about the area under the curve, I need to explain to you the sigma notation. So the sigma notation is a way to represent concisely what is, let's say, a sum written here in dot, 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 right? So in general, if I sum a sub k, so what happens here, this is like, if you program, it's like a while loop, right? So k starts with 1. So I have a1 plus, now k is updated to 2, plus k is updated to 3. K is updated sequentially, one integer at a time. You just add 1 to it until you reach n. And that's when the summation stops, okay? Let's see if you understand what I just said here. Suppose I want you to write the expansion. What is this sigma in sigma notation? What is this truly a sum of? Does it make sense? Write a, what it is. So here it's 1 over k. So again, what happens here is k starts at 1, then you put 1 here, plus, then k is 2, you put plus, and onwards. Make sense? I want you to write what this expression is going to look like.
Wait, the number on top is what?
So this is, again, all it is, a sigma notation is a shorthand, right? Instead of writing this, when you can write the summation in this form, okay? So this is a notation that tells you how to encode like maybe a very long sum.
So this is going to be written out 5 times? Is that what it means?
Exactly. So that means that we have, exactly. So Melissa, thank you so much. It's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, right? You understand? What happens is that you update the k and you add it up. So that's just a notation. It's just a convenient way of representing sum. And the others are very similar, right? So b, here what do I write? Here I begin at 3. So it's 2 times 3 plus 2 times 4 all the way until I get to 6, yes?
Right.
And onward. So this is, I'm summing, what is c, by the way? Can you tell me? C is very quick. K starts at 6 to 6 of k cubed. What is that?
K cubed.
So what does this sum is calculating? So Melissa, you're absolutely right. It's 6 to the power 3. It means k just runs starting at 6 until it reaches the stop value, updating consecutively, right? And you're just adding the number cubed. Okay, so k at 6 cubed plus next thing is this cubed, etc. Right? And then here again, you see, so a was, as I mentioned, it's 1 over k. It's just a shorthand for 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. We add them. Okay, you see that where you see the k, that's how the values are updating from first to second to third, etc. They run consecutively. So really, you see 1 through 5. Okay, essentially the sigma sign is just a kind of a placeholder. Essentially, you see k1, k5, and you see this thing, right? So you really look at the bottom number. That's where the integer starts. and that's where the integer ends, and it grows consecutively one after by 1 unit each time. Okay, so here again is k3 to 6, and notice this is a sum of even numbers. So it will be 2 times 3 plus 2 times 4 plus 2 times 5 plus 2 times 6, which ends up being 6 plus 8 plus 10 plus 12. And when I sum k from 6 to 6, I just only have one instance. I just put a 6 here, so it's 6 cubed. Yes, and when I start here, summation is j equal to minus 2 to 1 of j squared. Again, that's what I'm trying to say is first, you don't have to worry if it's k or j. This is a dummy variable. In other words, it's just an index of how the integer, where the integer begins and when it's over and what to do with the integer. So what is this a summation for?
-2 to the second.
So it's -2 squared and then plus next. What's the next number plus?
Negative.
Ooh,
But it's only once, no?
yeah.
No, it started at -2 to 1. So what am I right?
So
So it's
negative
negative?
1,
Yeah,
-1, 0, and then 1.
Yes.
I got
Right.
it.
So here it's what we truly. This is just a way to write 2 squared plus -1 squared plus 0 squared plus 1 squared. Make sense?
I understand.
Yep.
That means just the integer where you start, and this is the integer. It's bigger. It's the integer where you end, and you go consecutively. So you see -2 plus 1, -2 plus 2, -2 plus 3.
All the way to 1.
All the way until you reach this number, and you move consecutively. Yes.
Okay.
And now let's see how you would understand this sum. E. It's a summation from I equal to 2 to 6 of the number 5. What's the answer?
Oh, you have to know i's.
Yes, and here you don't see any I. So let me see what you interpret. You understand? As I goes from 2 to 6, you are adding this number. So David and Daniel, the answer is not 5. It just tells you, again, notice this tells you what to do at this step, right? At the -2 step, you square -2. At the -1 step, you square. So here we have at step 2, I put 5 plus. At step 1, at step 3, I will place again 5.
So is it 2 plus 5, 5 plus 2, 5 plus 3, 5 plus 4?
No,
Very confused.
there is only 5 here. What are you adding? So this means that the sigma is like a summation. The reason they say sigma, it's like a sum, right? It's like an S of sorts, right? So you are adding this value as I varies from 2 to 6, right? So the answer is
Is I referring to negative square root of 1?
no.
Oh, that's what I
Okay.
was saying. Okay.
No, definitely not, right? I also don't like to use the letter I. In your book, they use, I think, the letter I very frequently. I don't like to use it because I seems to have the reserved meaning of root of -1, right? But usually when you do that, you write I like with maybe a thick italic I, so that you know it's square root of -1. So I don't like to use I just try to show you that, again, there is no confusion because this already sets the meaning of this variable, right? If it's the fact that you place it here, and then that means that it must be an integer that's updated 1 unit at a time. So Juan, you say 20. So let's see. So that would be not quite right? Because it is 25.
Oh, so it is 5 squared.
No, but that's not by 5 squared.
Because we took the 2 and we put it on top like we did.
No,
2 squared. Oh, 2 to the 5th?
no.
What was it?
No, just one person told me the answer is 20, right? Right, guys, you see, think like a machine. So I'll show you now the answer, right? So think like a machine. What does it mean? It means the following. It means that as it's like a while I moves from 2 to 6, you are adding 5. You see, so I is equal to 2. This is what's happening. This is our machine understanding. When I equal to 2, you put this number 5, right? And then plus upgrade to I to the next level, right? I to the next level is I equal to 3. Now what happens at I equal to 3? I add this expression, so it's 5 again, right? Then I equal to 4, it's again
all
5.
The way to 6.
Right. So
okay.
that you see, so a computer will. So we don't add any 1 anywhere, right? This expression here, what it's just a count. How many times have I added 5, right? I added 5, 6 minus 2 plus 1 times, right? That's the count here. 6 minus 2 is how many after I equal to 2 that I added. I will explain that again.
Where did you get the plus 1 from?
Yeah, I was looking.
Yes. Why do I add up with plus 1? Well, again, right? I just see the count, right? So look at it. How many terms am I adding? Because I'm adding the constant number 5, right? How many times am I adding 5? I'm adding 5 from I equal to 2 to I equal to 6. Do you see it? How many times am I adding it? So if I take 6 minus 2, I get 4. What is 4? 6 minus 2 gives me those numbers, right? 6 minus 2 gives me the numbers following the very first expression. So 6 minus 2 is 4 plus the one that I missed, right? It's like, it makes sense? I'm going to explain this later again, right?
Yeah.
You see, get it? So the 6 minus 2 plus 1 is just a shorten. But first, you understand that it's just the summation of 5s a bunch of times.
Yeah.
As I varies from this number, that's what this is doing. As the integer starts here, all the way until it reaches this value, you're adding this expression. Right? In this case, the expression responds to the step. But in this case, the expression that I'm adding is always the same. Okay? And then final thing that I want you to do is just write out what is this, f. What happens here? S starts at -3 to 0, e to the 2s minus 1.
Okay. So an e to the 21 minus 1. So just go all the way to 0.
Yes, right? So, so are we ready? So this is a pretty simple question, I hope, right? It's just a notation, right? So what it is that I start at -3. So I have e. I see this is, I put -3 here, then I write plus, and I upgrade s to something else. If you know programming a little, so you say s equals to s plus 1 in programming. It means upgrade the number to a number bigger than it, right? So just like an algorithm that tells you to first put a -3 here, then put a -2 here, then a -1, then a 0, right? And add those things up. And those are adding, the powers are negative and odd. Okay? And let's try to see if you can go and write the reverse process. So next couple of questions, here they are. I want you to convert to sigma notation. See if you can do that. You understand? So here is a sum. I want you to write the sum in sigma notation.
Oh, this is so hard. I mean, it's really not, but okay.
No, it's really not. It's just you're learning just another sign, another notation to express the same thing.
Okay, let me try.
Professor, are you posting these yet?
Did I post the lectures? No, I wrote them pretty much like on the brink of our class. That's why we started late. I just barely finished writing and I scanned it.
Okay, so
I will post it after this lecture to my I want to say channel, but I mean website.
So you would have the sigma sign,
yes,
with a 7 on top.
Yes.
2 on the bottom.
And where s is equal to 1, I'm guessing?
Well, the summation is 2 plus 3 plus 4. There are many ways to write it, but the summation is this. I want you to tell me in sigma notation.
So we added 1 to each.
Yes, so but there you're right. But then if you say n1, then n is equal, the last n equals to 6, if that's what you're adding. So there are many ways of answering this, right? I would have started it at, let's say, k equal to, or n equal to 2, all the way to n equals 7 of n. Summation is of
which
the value.
Which is just 1, right?
Well, here is how I wrote it, right? I wrote it like this: k equal to 2 all the way to 7 of the expression k, which means first I put 2, then k is 3, and I write plus that new k plus k is updated,
okay.
right? You understand? So this is telling you how, with each step, the expression that you're adding is updated, and this tells you where you start, and this tells you where you end. And what Patel wrote, there is only one thing: the last number. If Patel wrote that I can sum here k plus 1, so let me possibly write what was written.
2 in the beginning, and
so
then it's like n
Patel
plus 1
wrote
and
this.
Yeah, the mashait kavantigo.
Okay, so this, and then you have n plus 1.
Yep.
You can start it like this, but then you have to place a 6 here, right? Because
So-
the last time is 6 plus, the last number when n is 6, it will be 6 plus 1, and that would be also correct.
So n can be just equal to 2, and then it's 7 on the top.
Yes,
That's what
you can, but the point, it's good that you mentioned it because we need to have all the expressions, right? We need to see that many different expressions mean exactly the same
You can
thing.
write it so many ways. That's so
Yes, yes.
okay.
They can write it so many ways, and that's going to be both a problem and a blessing, perhaps.
Right.
Okay.
So what about this one is more challenging? B, 1 plus 3 plus 5 plus 7 plus 9 plus 11. How do I write that?
I think I got it.
Okay. You can write either in text or in...
K plus 2.
notice it's 1, then 3, then 5, then 7, then 9, then 11.
So I was thinking you could have the 11 on top. K.
Possibly, but make sure that you see the numbers here, they have to K or whatever number you
I was
select.
thinking K plus 2.
But if it's K plus 2, let's say K it begins to be what? K is, what's the start point?
1.
So if the starting point is 1, so some people say 1, and then we have K plus 2, top is 9, right? So let's see if Ali is right.
Okay, yeah.
So
You would have
if
to have
Ali is
9
right,
on
it would be then 1. First the number is 3, then the
Yeah.
next number is 4, then the next number is 5, so it's incorrect.
No,
Ali,
but
right?
I'm saying
Then
you
would it
could
be
have
negative?
9 on top.
Sorry? 1 second, guys. Apologies. Sarah and then Arham. Sarah, what do you want to
Okay, I
say?
just saw in the chat that you could have 9 on top, K plus 2, and then it would go up to 11. So
Yeah, but it will not go through the numbers 1, 3, 5, 7, 9, and whatnot, right?
If
It,
you have-
it will it will go
Oh.
like this. Look at it. If Ali were right, so first of all, if I put K equal to 1, and then you say K plus 2 is the region, right? Then we begin at 3, first of all, right?
right, wouldn't begin at
So we begin first at 3. If K
Right.
begins at 1, and then we add K plus 2, so we first add 3. Then K equals to 2. It's updating all the way consecutively to 9 through
Yeah,
both
makes
even and odd numbers. Then when K equals to 2, then I'm adding 4. So it will be 3 plus 4, but I'm not having a 4
Uh-huh.
here. I'm having a 5, right? And then it will be, K is now upgraded to 3. So it will be 3 plus 2. Then I have 5, right?
K
So
minus
K
2.
plus 2 is really what? Up to 9. It's a sum of consecutive integers starting at, okay.
minus
And now,
2.
Yuan, you are correct.
Oh, okay.
Except you don't want to, yes, so Yuan is correct.
Yep.
You can start n at 1 and top
Minus
be 6 of 2x minus 1, because if you take an integer, multiply by 2 and subtract 1, you make the number odd. Okay. So here is I did it differently. I did plus 1 and I started at 0. It's the same thing, right? So my solution is start K at 0 and go all the way to 5, and then double the number and add 1. So let's say at 0, 2 times 0 plus 1 is 1. Then when K is equal to 1, it's 2 times 1 plus 1, which is 3. When K is equal to 2, it's 2 times 2, which is 4 plus 1, which is 5. You understand? So I started at 0 and all the way to 5.
So this is
And-
the number in between those two, that number 2k plus 1 is the function.
Yes, it's the function of each step, right? So I stay at step 0, put 0 times 2 plus 1. At step 1, put 2 times 1 plus 1, and all the way until 5. How do I know the last bottom? It's very simple, right? I have to plug it in here. 2 times 5 plus 1 has to be 11, right? So 2 times k plus 1 is 11, and I can solve for k, and that's how I know the top bottom. And Yihuan suggested an entirely correct procedure, such as that it start n equal to 1 until 6, and of 2 times not x, but 2 times n minus 1. That's also the same. You see? So I can write it like this. I can write it if you want to use n. I put 1 all the way to 6 of 2n minus 1, right? And that also works perfectly, right? 2 times 2 is 6, 12, sorry, minus 1 is 11, right? And that 1, it's 1. Good, right? So, and for C, that's good that we solved C here. I'm sorry that I revealed it possibly, but wonderful, right? Good. So now C is the addition of even numbers, 2 plus 4, 2 plus 4 plus 6 plus 8, right? So what am I really adding? I can write it like this, k equal 1 to 4 of 2 times k, correct? Because then first number is 2 until the last number, I see all of them are even. So I can get even numbers by multiplying just any integer by 2. So 2 times 1, 2 times 2, 2 times 3, I'll get consecutive even numbers. All the way to 4 because I need to get 2 times k equal to 8, which means k has to equal to 8 over 2, which is 4. So it's k1 to 4. And you can write it, you can reset it. I can say k equals 0 all the way to 3 of 2 times k plus 1, right? There are many ways I can write the same expression. Good?
I hear there are multiple answers.
They are the same answer, just they're synonymous answers. They're describing the same procedure, but using different.
Yeah, but you have to be so careful.
Well, usually you should be able to very quickly see that they are the same expressions, right?
Yeah.
We will try to train for that. Now, explain to me how I represent D. I'm adding a bunch of minus 2. Minus 2 added to itself 4 times. Write it in sigma notation, please. You can tell me simply bottom, middle, and top. All right, and you can give me the information by text if you want this way.
Isn't this the same as the equal to the I to the 5?
Well, sure, it's very similar, right? So you can use any letter you like, right? I tend to prefer the letter K, but that's I don't like using letter I avoid it as much as I can.
-2.
Right, -2 is what? So we are adding -2 to itself 4 times. So describe this procedure with the sigma notation.
So -2 is going to be on top.
No.
No?
No, it
No.
depends. You can make -2 on the top. You can do it if you reset your.
Oh, correct.
You can make the top and bottom any numbers. You just have to then specify a different formula.
Right.
I need to know if you're correct or not. I need to know bottom, middle, and top. So
Okay.
Melissa tells me bottom is 1, middle is -2, and top is 4, and that's beautiful. Melissa, you're correct, and Patel, that you agree you're correct. Okay. So I could do it other ways, but the simplest way is. First time I add, second time, third, fourth, right? So I will make k go from 1 all the way to 4, and the middle part is the expression I'm adding. So that would be -2. Good. So here is that answer, right? What Melissa said is k1. That's bottom, middle, -2, top is 4. Okay, so it's -2 plus -2 plus etc. Right? And then what about just do a few more? Now we are up to E. Tell me what's the sigma notation for E. Again, you can text simply bottom, middle, top. David, so you say bottom is 2, middle is 1 over n, top is 4. Wonderful, right? And then your summation goes through n. Bottom k1, if you say k is middle, guys, and Melissa, middle, you probably want to use the same notation, 1 over k plus 1. If you're using k, then the middle must be a function of k. Yeah, but that's otherwise very good, because the computer would have just added 1 over n plus 1, 1 over n plus 1, 4 times, or 3 times, sorry. No, I understand, Melissa, just making sure. Computers can be extremely annoying with it.
What is that number? What's F say?
F is 1 over 4 plus 1 over 6 plus 1 over 8.
Okay.
And, right.
Wait, I have a question. Why wouldn't the top be 3 and then it will be 1 over k and it will be k equals 2? Why can't it be
For which? For E?
Yeah, for E.
For E, you can make top and bottom any numbers you like. You just that would upgrade the middle function, right? So you just so you see easiest I see it begins consecutive upgrade is from 2 to 3 to 4. So easiest I think to write bottom is 2, top is 4, and middle is 1 over k, right?
Yeah,
But I could also write bottom 1 and top 3, and then middle is 1 over k plus 1. Make sense?
Yeah.
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 Yes, but so I'll get to H. I noticed you spoke of H. We're gonna get there. I think you are correct about H, but I'll be sure in a moment, right? Maybe I'm wrong. No, I think so. There is a mistake. Yes. You mean square. Wonderful. I think you did H correctly. So what is we did E, right? Everybody understands E. Now F.
Can I say F? Can I say F? I haven't said
Go ahead. Say F. It's quick.
It's 3 on top, 1 over k plus 1 in the middle, and k equals 2 on the bottom. No, k equals 4. K equals 4.
So you can be careful. If you put 3 on the top.
No, k plus 2. K plus 2.
If it's k plus 2, it will run through even and odd numbers. Notice we're only running through even numbers.
So that's k plus 1.
K plus 1 will also run through consecutive numbers, right? How do you make it run through even numbers? It's 4, 6, 8. We have 3 even numbers. You have to make it run through consecutive even numbers. So do F. And then when you say k plus 1 or k plus 2, then was k upgrades? When k is even, k plus 2 is even. When k is odd, k plus 2 is odd. But you cannot have odd numbers in this summation. So bottom 2, top 6. No, because David, if you're talking about F, and I think you're talking about F, look at what happens here. If I put the number 3, instead of k, then I have 1 over 5, and I don't have 1 over 5. You see?
That's what has to be multiplication.
Right. Top, guys, you see, if you just tell me bottom or top, it doesn't tell me anything. I can write the summation with top. As soon as you tell me top, I can figure out bottom, and I can figure I can figure middle expression. It's possible to write the summation where the top equals to 3. Right? I can do that. I can take if you tell me the top, I can figure out the bottom and middle.
Why isn't it 3 on the top and k equals 2 and on the bottom, and then on the middle is 1 over k plus 1?
Because then first of all, k plus 1 means you're running through odd numbers, because when k is even, k plus 1 is odd.
So then can it be k equals to 3? No.
Yeah, so you have to make sure that it runs through even and only even numbers. If you say something like k plus 1, then I right away see it will run through odd numbers. All right, so come on, ready, guys? How do you make this thing go through only even numbers? That's not so hard. I think Juan, you had a typo, right? Because what is 1 over? Yes. Come on. Something? Come on. We are doing F. But if you are above it, or if you move faster, you can do F, H, and I, right? As quickly as we can, I want to move through this. Wonderful. All right. So David, you got it. So that was F. Yeah, F, right here. F. Right. So simply start K at 2 and go to 4. Right. So what do you have? You have 2 times 2, then 2 times 3, which will give you 6. And then afterwards on the denominator, 2 times 4. Right. So K is 2, it's 2 times 2. K is 3, it's 2 times 3, which is 6.
It's
very
fun. It's like a game.
Yeah, it's yes, except it can be truly very, you see. So those are going through even numbers is fairly simple. Then you can make it hard. Now what about H?
Patel, hop in.
I did it, but I don't know if it's right.
I think if I saw where is it? I'll scroll up. You're right about the bottom, but you're not right about the top. Aside from that, I think you are correct. So you notice 4, 9, 16, and 25. They're all what? What's common to those numbers?
They all are perfect square roots. They're all
perfect squares, yes.
Perfect squares, yeah.
Beautiful, right? So we have already a few numbers, right? So
be 2 to 5.
Right, 2 to 5 is the simplest way to put it, right? So top is 5, bottom is 2, and middle 1 over k squared is what Melissa says, right? So yes, so that's right. And then okay, so let me just show the answer in case you don't follow right here, right? If I first square 2 and you get 4, and then I square on the bottom 3, and then I square 4 on the bottom, and I square 5 on the bottom. So it's 1 over k squared, where k goes from 2 to 5. So Melissa and Batel and David, I think, and a bunch of people, some small mistakes maybe here and there, but and Juan, all of you are correct, right? So Juan likes to start it at n equal to 1. So all of those are correct answers. Now, finally, what's the answer to I? 3 plus 6 plus 9 plus 12 plus 15 plus 18. What's the answer to that? So top, where is it? Yes, top 6 and 3k. Yes, agree. Wonderful. All right, so you got it. So yeah, it's 3 times k, where I can start it. It's at k equal to 1 all the way to 6 of 3 times k. Those are multiples of 3, consecutive multiples of 3. Good. So here is, you can make bottom 0, middle, well, careful, David, right? You're always tempting, when you say k plus 3, you're making the numbers run consecutively. So maybe it will start from 3, but the next number will be 4. And the next number will be 5. You see, when you say k plus 3, the numbers do start at 3, but they run consecutively to 15, which is not what you want. You skip a bunch, right? You have 3, then 6, then 9, etc.
Yeah, I see.
Yes, it has to be multiples of 3, because if you say k plus a constant, it just you're starting the ruler and moving by integer increments, 1 unit increments. Okay, and here is again remark is, if you look at the very last expression, there are again many ways of writing it. One first thing is that the letter k is, again, it's a dummy variable, right? K is just telling you basically what I see here is, this is the first number, the last number, 3 times the step, right? So this tells you what's the step, this tells you what's the last step, and this tells you what to do at each step. And you can use any letter to describe it, right? What matters is that this is just telling me at step I multiply by 3. Okay, at step k multiply by 3. And another thing to note is, again, right, there are many ways to, even if you use the same letter, you can start the sum at any number. So for example, if I have the sum of squares from 1 to 6, that means you sum all the square integers from first square integer to the sixth square integer. So that would be 1 squared plus 2 squared all the way to 6 squared, right? That's what this truly means. When you say this, you imagine this expression. What you see, but I can make the top number anything I like. I can make the top number not 6 but 8. If I make it 8, then what I'm squaring is k minus 2 squared. Understand? Because what matters is it's at the third step, take third step, subtract 2 and square it. It's like you're getting back to the first step. Third step, subtract 2 and square will give you the same thing as first step square. So those two sums mean exactly the same thing. Make sense? Many ways. You should be able to look at it and say, oh, it's not this notation. What am I doing here? I'm just adding, in both cases, consecutive squares of integers. Okay, and then let's maybe quickly talk about some basic properties. So the following properties for sigma notation are pretty obvious. If you start k at m and end at n, the sum of ak plus bk is just the sum of the ak's plus the sum of the bk's separately. And why is that the case? Why is 1 the case? Well, very simply, what does this mean? This means I first plug in m, then I plug in m plus 1, and then I plug in n plus 2 all the way until I get to n, right? And addition, I can decide to add all the a terms first and all the b terms second. So I can regroup, right? So the summation means I put k equal to m, then I make then I add where k equals to m plus 1, and I continue adding. So then when I break it apart, I have the a's and b's separately, yes? And so then we have, this is in sigma notation, the sum for a, and the second part is the sum for b. So it's very obvious why this is true. It's just summation. Good. Similar thing is I can always factor, if I have constant multiplying each ak, I can move the constant outside. And that's why, because the summation where k goes from m to n of c times ak is cam plus cam plus 1 all the way to the very last term. All of them are multiplied by c, so I can factor out the c. And I have c multiplied by the sum, which is c by the sum expressed in sigma notation. You follow me? And the next topic, we might, I don't know, we do need to go through quite a lot of things. I was hoping to cover the full lecture. All right, Zina, take care. You remember, guys, I'm going to return, hopefully, your exam 1 by the end of the weekend. I would like all of you that have not submitted the exam, if you can, please submit it. Make sure that it's good. Okay?
Thank you, Professor. Have a good night.
Yes, okay,
Professor,
have a
you
good
wanted
night.
to talk. I have a couple of minutes. You wanted to talk?
Yes. So we will, guys, I'm going to stop the recording. And if you want to, we will continue talking with those that want to continue talking.
I have like 5 to 10 minutes.